Welcome to Study Loop.
We're told we have a hydrogen atom in the 1s state placed in an external magnetic field in the z-hat direction. The temperature T is 300 Kelvin, and the spin quantum number m sub s is going to be plus or minus a half because we're dealing with electrons. So we know the formula for potential energy, U, is equal to 2.00232 mu sub b, Boltzmann constant, times m sub s times the magnetic field B. Well, m sub s here can be plus or minus a half, so the difference between the potentials when u plus here is when m sub s is plus a half, and u minus is when m sub s is minus a half. We subtract those from one another. Since both terms are going to have this 2.0023 mu sub b times m sub s, mu sub b, since both are going to have that, and both term to b, we can pull that out. So really you're subtracting the m sub s terms. So this is 1/2 minus negative 1/2, which is equal to 1. So since the theory from the chapter says that the number of atoms in a given state, n plus, divided by the number of atoms in the n minus state is equal to the exponential to the negative difference between the two energy states, which we have written above here, again, where 1/2 minus negative 1/2 is 1, divided by Boltzmann's constant, K, times the temperature, T. So plugging in mu sub B, being Bohr's magnetron number of 9.274 times 10 to the minus 24 joules per Tesla, plugging in our value for the temperature, and then plugging in the value for the Boltzmann constant, K, of 1.38 times 10 to the minus 23 joules per Kelvin, we get negative 4.48 times 10 to the minus 3 inverse Tesla times the magnetic field number, or times the magnetic field B. So for part A, let's switch back to, for part A, we are told that the magnet B is equal to times 10 to the minus Tesla. So if 5 times 10 to the minus 5 Tesla, our ratio, the number of positive to the negative spin, is going from plugging our value of B into this expression up here. So we just plug B into this expression, and we find that this is equal to 0.9999. It's almost a 1 ratio in a small magnetic field. Okay. For part B, we use a different magnetic field. Here we're asked to use a value of equal to 0.5 Tesla. So plugging that in, we find the ratio of minus is equal to 0.9978. And then finally, for part C, we're using a value of the magnetic field equal to 5. Since this is several orders of magnitude than what we used in part A, and an order of magnitude larger than what we used in part B, that the number negative spin atom is going to again decrease. And minus, plugging into our expression, to equal 0.978. We can box it in to our question.